Hello and welcome to Warsaw University Astronomical Observatory Tuesday series. We begin our semester with a series of talks on gravitational waves. And today we have an honor to host Professor Sathyaprakash Bangalore. He did his studies in India, obtaining his PhD in theoretical physics at the Indian Institute of Science. He currently is an Elsbach Professor of Physics and Professor of Astronomy and Astrophysics at the Penn State University in the US, and also holds an affiliation at Cardiff University in the UK. Since the 1990s, he has been a member of the major gravitational wave experiments, GEO and LIGO. And he's one of the leading members of the Gravitational Wave International Committee, where he developed the science program for the next generation instruments like Einstein telescope and Cosmic Explorer. So Satya has kindly agreed to open this semester's seminars with a review on the hottest topic of astronomy, I think, these days, gravitational waves.
Their efforts. So thanks to all the PhD students and postdocs for making this possible. And I'm sure we'll continue to benefit from their input and exploration. Today I'm going to be talking about gravitational wave science that is made possible by ground-based detectors, in addition to the frequency explored by ground-based detectors, which is essentially in the audio band, something like 10 hertz or even 1 hertz, all the way up to something like 10 kilohertz. You can think of this as gamma rays of gravitational wave window. In addition to that, we have optical window explored by the laser interferometer space antenna, and even radio waves that are being pursued by pulsar timing arrays. I won't be talking about radio or optical. I will be talking about chiefly gamma rays, and that means the audio window. And to explore this, we have a number of detectors that are already taking data for a number of years, something like 20 years now, 2 decades. In the US, there are LIGO Hanford and LIGO Livingston. And in Europe, we have a smaller detector compared to LIGO, which is 4 kilometers, GEO 600, which is 600 meters, and Virgo, which is 3 kilometer arm length. The length of the interferometer is like the diameter of a telescope. The larger the length, the greater is the sensitivity. And so it's really a very good example. And from what used to be a prototype at 40 meters, we went directly increasing it by a factor of 100 to 4 kilometers with LIGO observatories. This is unheard of in astronomy. In astronomy, normally to double the size of a telescope diameter, it takes roughly 40 years. And this took about, I would say, 20 years. But the next step, another 20 years, we will increase it by another factor of 10 to 40 kilometers or 30 kilometers, depending on where it is being built. And that would be remarkable because such revolutions happen over something like 150 years in astronomy. And most of the reason for this is because the cost of increasing the length of a detector is linear, whereas in the case of telescopes, it's like the square of the diameter, the quadratic. And that makes a lot of difference in being able to build detectors that are more sensitive pretty quickly. And I'll show you some slides, what are the consequences of this. So in addition to these yellow sites that you see, which are operational, we have Kagra, which is currently actually taking data. I should change that to LO2. It already took some data, but it is further being commissioned to reach its design sensitivity in the next few years. In addition to all these, we have LIGO India, which was planned when this slide was made, but the project was approved soon after the first discovery. In fact, just a few days after the announcement, the Indian government approved the project. The construction should begin sometime soon. Let me take this opportunity to tell you that, if you have any questions, I don't mind any clarifying questions. If you have to raise your hand and ask, I don't mind being interrupted. Before I go on to describe what gravitational waves have done for our understanding of the universe, I want to spend one slide on telling you what is it that we are measuring with gravitational wave detectors. So if you look out from the sky, what you generically see is a gravitational wave that is in general relativity composed of the two polarizations, plus and cross, shown in this middle sketch, showing how the force field due to a gravitational wave changes depending on whether it's plus or cross polarizations. So we have to measure the two polarizations, H plus and H cross. In addition to that, we have to, let me call it mixing angle or polarization angle between the two polarizations that a gravitational wave detector is sensitive to. That is called psi. Let's call it polarization angle. And then the position on the sky, theta and phi, is what we have to measure. One can equivalently think of measuring the distance.
Join the meeting.
And the orientation of the source relative to us, plus the other three. So there are 5 parameters that you need to measure, generically speaking, and they are the ones that affect the amplitude. As you can see, we really can't measure the distance unless we make all these 5 quantities, measure all these 5 quantities. And to do so, you need to have 5 measurements, and that is enabled by 3 non-collocated detectors. What happens with 3 non-collocated detectors is that you get 2 independent time delays from the 3 detectors, but also 3 amplitudes. Because if the detectors are located at different positions on the surface of the Earth, they are sensitive to different combinations of H plus and H cross. This way, you will measure H plus, H cross, and psi. Einstein telescope is special. It's able to do it even though you are at a single position. I'll come to that if necessary later in the talk. But the timing allows us this measurement of the position on the sky, theta and phi, and H plus and H cross and psi are measured by measuring the amplitude of the incoming gravitational wave at 3 non-collocated detectors. So that's the way we can measure the distance and the orientation of the source, and that's very important. Now, how do we then extract the masses and the spins and eccentricity and so on? Well, this is contained in the shape of the detector output that we are searching for. What I show here is without any detector noise, the signal that might be coming in from the sky for 2 examples. On the left waveform slide, you have a non-precessing binary. It has a non-zero mass ratio. And because of this, it can contain some higher modes, which are important to things that we are going to talk about later. I'll come back and explain what I mean by higher modes in a minute. So if the source is face on, you have one pattern, the blue pattern. This system is spinning. Both the black holes have pretty large spins, and it is 1:4 mass ratio. And you can see that the patterns are pretty different. And that's what we are sensitive to. Whether you are face on or edge on, you have different kinds of waveforms coming in, but they're not too different. You can trade, the inclination to distance and get one from the other. But the spins will induce further pattern in the waveform as shown on the right-hand plot. If it is face on, you're still not sensitive to any precession. However, if it is oriented at an angle, it will induce spin modulations, spin-induced modulations. And therefore, we'll be able to extract information about masses, which tell you how quickly this waveform frequency is changing and how long it lasts. Those are the 2 parameters which will determine the masses, and the modulations further will tell us about the spins. Normally, for ground-based detectors, we don't have to worry about the eccentricities. So in all, we have to measure 15 parameters, assuming general relativity is correct. And we are able to do that with at least 3 non-collocated detectors, which is the reason why LIGO and Virgo began cooperating right from the beginning, right from the word go. And so we have, in addition to that, matching the detector output with the expected waveforms that will give us all the other parameters. So, okay. With that, let's go on to talking about very quickly a summary of what the first and second observing runs have taught us. However, I won't spend too much of time on this. So the first observation was on 14th of September 2015. Detection was enabled by, and characterization was enabled by match filtering, which required development of very accurate waveforms in general relativity for more than 3 decades, including numerical simulations. The masses that were detected for most of the people in the world were somewhat too large, but not for the Warsaw group. For the Warsaw group, this 29 solar mass and 35 solar mass is pretty much something that is possible. However, it was considered to be a challenge to astrophysics, but the challenges keep on increasing with more discoveries, as we will see. But as I said, let me be very clear, it was not a consensus that these heavy black holes cannot occur. It was only a minority that felt that they can exist, but they were right in thinking so. Anyway, the black hole masses were initially thought to be so high that it generated interest. Maybe these are not formed by stellar processes. They are formed in the very early universe. They are primordial black holes. A subject which had remained dormant for decades became suddenly extremely active when it started to be realized that these may not be explained by astrophysical processes. Now, I won't say much more about this first discovery, but 1708-17 is considered to be, which is discovered on, of course, 17th of August, 2017 by LIGO and Virgo, is considered to be a gem of a discovery because it started off multi-messenger astrophysics with the participation of gravitational waves. So what is this? On the top, you see gamma ray bursts observed in coincidence with gravitational waves. The lower plot shows you gravitational waves, and the upper plot is showing you gamma rays, and there is a delay of something like 1.7 seconds between the peak of the gravitational waves when the 2 neutron stars merge. This was recorded by gravitational wave detectors, and the gamma ray was recorded by Fermi, but also by IPN. And these enabled us remarkable new signs. The host was localized to a galaxy called NGC 4993, and immediately one could observe the afterglow and the EM counterpart due to this merger, which lasted in infrared and optical for only a few days, but it was visible in radio for many, many years. I think they're still taking, in radio waves, they're probably still taking data. Okay, what did this do for fundamental physics? If you look at the delay between gamma ray bursts and gravitational waves, and you think that, oh, they were both emitted at the same time, then how quickly did they travel to us? Then you can determine the speed of the two by looking at just the ratio of the delay to how long it takes for the waves to arrive from there. So the distance to this object is about 40 megaparsec. Divided by the speed of light tells you how long it takes for the waves to arrive. And the ratio of the delay, 1.7 seconds that we observe, to the time it takes is about a few parts in 10 to the 16. That is the limit that you should be able to set by doing a detailed analysis. It is slightly worse than that. At the lower end, it is minus 3 into 10 to the minus 15. At the upper end, it's 7 times 10 to the minus 16 for the difference in the speed of gravitational waves compared to the speed of light. This relative speed measurement immediately ruled out many alternative theories of gravity that were proposed to explain dark energy. There are still some possibilities of alternative theories, but immediately after this, many theories were ruled out. In addition to that, general relativity allowed pretty accurate prediction of the waveform, because of which we know that they are neutron stars. We don't really, from general relativity, we can't immediately tell whether it's a neutron star binary or a neutron star black hole binary. I will talk about that in a minute. However, the afterglow that was observed allowed us to verify whether or not heavy elements were produced. You know, this ball of neutrons, when they collide, they produce extremely energetic neutrons that are flying apart in the ejecta. And these lead to what is called the arc process production of heavy elements. And it is believed that merging neutron stars are responsible, if not for all, but for a pretty good fraction of the heavy elements that we use in sophisticated devices on Earth today. And today, we know because of this observation that some of it was at least produced in merging neutron stars. Now, another very important thing was about measuring the distance. As I mentioned right in the beginning, we can measure the distance if you use 3 non-collocated detectors. And it turns out gravitational wave observations of binary black holes and binary neutron stars can give us very accurate measurement of the distance. And for this reason, they are called standard sirens as opposed to standard candles, because gravitational waves are like light. Sorry, gravitational waves are like sound. They are more analogous to sound waves than the light from electromagnetic observations. Anyway, because of the fact that these are standard sirens, if you place the source farther, their observed luminosity goes like 1 by r square. This allows us to measure the distance accurately, and it helped us to measure the Hubble constant. And the obtained value covers both the CMV measured value, which is below 70 kilometer per second per megaparsec, as well as the shoes measurement that is shown in this slide. However, we are not able to tell which one of them is correct. And one of the goals for future is to resolve this discrepancy or problem with the Hubble constant. I'll talk about that a little bit later. The final thing I want to say that came out of these detections is understanding dense nuclear matter. You know, neutron stars at their core consist of matter which is likely several times the nuclear density. Depends on what the mass is. Higher the mass, greater will be the density at the core. And determining what is the equation of state and the composition of neutron stars at their core is an important goal for physics in general, but in particular for X-ray and radio and astronomy, as well as gravitational wave astronomy. The very first observation of gravitational waves determined the radius to be somewhere between 9 kilometers to about 13 kilometers. This is about 4 to 5 kilometer uncertainty, and there's a lot that needs to be done before we can say whether or not the core is composed of just hadrons, or if there are other types of particles that are present here. Okay, now we're going to go on to talk about LIGO Virgo discoveries in the third observing run. Let me go in a chronological order, starting with 1904-12, which was discovered on the 12th of April, 2019, just last year, 1.5 years ago. The signal was observed. The top animation here, which is probably not coming along very well, shows the numerical simulation of what the system might have done. And if you observe carefully, you see that the orbits are probably not completely aligned with the spins, or the spins are not completely aligned with the orbit. But the signal lasts for many, many cycles in band, and therefore we are able to measure various quantities pretty accurately. The signal was observed in all the 3 detectors, producing signal to noise ratios of 8.6, 15.6, and 3.7. This is the first ever binary black hole that we detected with definitively unequal masses. Equal masses is ruled out by a pretty large confidence. So that's the first observation. So that's the reason why it hit the headlines. But there is also significant non-zero spin of the primary. The primary is probably spinning at something like between 0.2 to 0.6. This is the dimensionless spin magnitude, and pretty well constrained away from 0. And because of the fact that this system had unequal masses, it emitted gravitational waves in not just the dominant quadrupole mode, but also higher order multipoles. Let me say what that is. So if you look at gravitational waves that come from the sky, as I mentioned before, it consists of the 2 polarizations written at the bottom of the screen as H plus minus IH cross. But it is really composed of not just L equal to 2 quadrupole mode. In principle, it consists of infinite sum of many multipoles, quadrupole, octupole, sextupole, and so on. But the dominant part is really the quadrupole mode. Unlike in electromagnetic waves where the dominant mode is dipole, there is no dipole radiation in general relativity. The quadrupole occurs at twice the orbital frequency, and for reference on the right-hand top plot, that corresponds to alpha equal to 1. But these higher order terms that you see in the bottom slide, which is simply sum over spherical harmonic modes for a spin 2 field, that will introduce other frequencies in the gravitational waves. And these are multiples of the orbital frequency itself. So, which means as far as alpha is considered, it is 1/2 equal to 1, equal to 1.5, and so on. So all half integer multiples of alpha are in principle allowed. And so one can do a test of general relativity by asking the question, is there any radiation in between at other frequencies? We are not able to do that at the moment. We can't do that test because the signal is not loud enough. However, we see a clear evidence that there is power at alpha equal to 1.5, which is the octupole mode. I never thought that I will ever in my life observe higher modes of gravitational waves. So this is really pretty phenomenal from what we have detected. Not only did we detect a source with higher multipoles, but we were able to firmly place constraint on what that is, whether it is in accordance with general relativity or not. We can't say, and by the way, what is shown on the top right corner in what is termed as off source is measuring the multipoles at other times when the signal was not present in the data. So that is just noise. As you can see, it is simply uniformly distributed around 0. However, when you look at the strength of the quadrupole, it's very high, but the strength of the other modes, 3-3 mode, is also pretty high at alpha equal to 1.5. In addition to that, this system, as I mentioned during the animation, seems to demonstrate some in-plane spin. That is, if you take the orbital angular momentum, the direction of the orbital angular momentum, perpendicular to that, of course, is the plane in which the two black holes are orbiting. And it looks like there is some component of the spin of one of the black holes in the plane of the orbit. This is what is responsible for precession. And so this is also the first time there seems to be within 90% confidence interval, which is marked by vertical lines in this graph. But irrespective of which model you use, there seems to be evidence for in-plane spin. And that's also another thing which is remarkable about this event. So let me now move on to the next event, which is the second binary neutron star event that we ever discovered. So here what you have is two, what we believe are neutron stars. We can't tell from gravitational wave observations. But if you take the masses that we measured and simulate, then it produces two neutron stars that are going around each other. They come together and they merge. And most likely, they immediately collapse to a black hole without leaving any electromagnetic counterpart. That's what we think, and I'll tell you the reason why that is the case. It was probably because of this that there was no ejecta, there was no EM counterpart, but we cannot be 100% certain because this system was about 3 times farther away than the 1708-17 event, and moreover, the sky area was pretty large and it was not localized very well. Maybe the combination of these two, even if it produced ejecta and an afterglow, maybe it was not very bright, and also the system was very far away and the sky was very big. So what are the characteristics of this neutron star, binary neutron star event? I think this is another surprising event when you compare the total mass of this binary to the galactic binary neutron stars. On the left-hand side, what is plotted is the significance of this event. It's not a super loud event. It is shown as an orange star compared to the noise background, which is shown with these contours in white and blue, are noise-produced triggers. Whereas the events that we have detected, the 1904-25 and 1708-17, these are pretty bright compared to the background. So there is no doubt that this is a real astrophysical event. But the surprising thing, as shown on the right-hand plot here, is that the total mass of this system is unusually large. What is shown in the white dashed line is a distribution of galactic binary neutron stars, a fit to that. And they are mostly, below 3 solar mass total. There are some that are even lower, 2.5, far lower. But none of the binary neutron stars in our galaxy have such a high mass, which is indicating to us that our galaxy is probably not a typical galaxy when it comes to the population of neutron stars. So 1904-25 is a pretty heavy system, and it probably immediately merged to form a black hole in the so-called mass gap, a lower mass gap, where the theory says that most likely you cannot produce black holes in that region. Nevertheless, nature knows how to produce it, even if stellar processes cannot do it. There are other ways of forming black holes in the mass gap, and these heavier black holes, lighter black holes, could find a way to merge with other black holes that might exist in the same environment. This is important for the next system I'm going to be talking about, which is a system that was discovered on 14th of August, 2019. The distance to this is about 800 million light years. And this is the first system in which we have two companions that are widely separated in masses. One of them is about 2.6 solar mass, and the other one is about 23 solar mass, a little heavier than that. But the lighter object has a mass that is neither possible for a neutron star. We talked about just now black hole being produced by combination of two neutron stars. Maybe it's a black hole that is produced by a previous merger, but maybe it is the heaviest neutron star ever known. What is plotted on the bottom middle plot is the companion masses. As I already mentioned, the primary is about 23 solar masses, but the secondary M2, which is plotted again on the top right with all sorts of distributions here, the pink distribution there, the magenta pink distribution that you see is the secondary, the posterior probability distribution for that. And the vertical pink lines tell you what is the 90% confidence interval. What you see is that the heaviest neutron star that might have been produced in the galaxy is much lighter. It's about maybe 2.1, 2.2, or even 2.3 for one of the candidates, but there are no neutron stars that are known in the galaxy that are produced. So that white band there is a questionable one, but probably, even if you take that to be a candidate, this neutron star here, the secondary, if you want to call it a neutron star, is the heaviest neutron star. In fact, the maximum mass inferred from previous observations by LIGO Virgo collaboration or Alsing et al. I have shown both of those in green and blue. These distributions are also, this is the maximum mass really, have only at the tail end of the distribution might be consistent with the heavier neutron star here. So this is a pretty remarkable object. If it is a neutron star, it's the heaviest neutron star. On the other hand, it could be a black hole that may form by usual stellar processes. We really don't know. Or it could be the merger remnant from a heavy neutron star binary, which could be even larger than 2.6. Or it could be a primordial black hole. We really don't know which one of these possibilities is true. As you can see, we are already seeing more and more exciting discoveries by LIGO and Virgo. In addition to that, due to the large mass ratio, this system also exhibited pretty large modulation of its signal and produced higher multipoles. Before that, so just to recap, we have two masses, 2.6, 23.2. Lighter companion is a mystery object, but because of the high mass ratio, something like 1:9, 1908-14 represents possibly a new class of compact objects. And considering that we have seen one of these objects over the past few years, the rate of events from this object is between 1 to 23 per year per gigaparsec cube. This is the most precisely localized source when it came to online determination of the localization, 18.5 square degrees, and also very well measured. The distance, given how far it is measured to a pretty good accuracy. 240 megaparsec is how far it is, and it is plus 41 minus 45 megaparsec. There is a clear signature of higher multipoles. I want to show you a graph of that. On the right-hand side, you see on the top detected data in light red or orange, and then in almost white patch, you see the estimation of what the waveform is by using one of the waveform models. It's called phenomenological waveform. That is the posterior distribution of what the waveform should look like, 90% credible interval. And on top of that, there is also a black patch, and that is from model independent fit to what the waveform is. In particular, from the phenomenon model that is fitted to this, you can see already in the signal a pretty clear significance of the modulation. And this modulation, detailed analysis shows, is not due to precision, which is what I was showing you in the introductory slide, but most likely it is due to the higher modes that are present. And in fact, as the bottom slide shows, we went ahead and measured what is the total amount of energy due to precision and due to higher order mode, the octupole mode. And we found no statistically significant power in precision. However, and it's completely consistent with noise distribution, as you can see on the left-hand side, whereas the amount of energy in the higher modes is pretty large, pretty significant. To give you a comparison, the amount of energy here is almost as much as the October 12th event that was seen in the first observing one. I think it was 15, 10, 12. That event has that much energy. So this is even more satisfying to see the presence of not just the octupole, but consistent with generativity. To me, one of the biggest surprises that came out of this event was actually none of these. All of them are glorious, that's all fine. But it is the left-hand plot. What you see on the left-hand plot is what we call a spin disk plot. So the left side of this plot is for the primary companion, and the right side of this plot is for the secondary companion. Let's just focus on the left of the plot. The distance from the center of that plot tells you what is the magnitude of the spin. And the angle tells you how much it is tilted. If it is 0, that means it is aligned with the orbital angular momentum. If it is 30 degrees, it is misaligned by 30 degrees with respect to the orbital angular momentum, and so on. It doesn't tell you the phi, but that's okay. It tells you just the tilt angle. What is remarkable is that the secondary of this, sorry, the primary, the heavier black hole, seems to have spin equal to 0. That means a Schwarzschild black hole to a pretty good accuracy. Almost all of the posterior is concentrated around 0. We can't measure the spin magnitude of the secondary very well. It is, it is anything between 0 and 1. However, the primary companion seems to be 0 spin. I know that there are astrophysical models, but again and again, to me, the fact that we are measuring spins that are consistent with 0 is a remarkable aspect of our discoveries. I'll say one more thing about that a little later. Let me come to the final event that has been announced so far, which was discovered on 21st of May 2019. What you see here is the bandpass filter applied to the data. The data itself is shown in blue for the 3 detectors, Hanford, Livingston, and Virgo. However, what you see on the top 3 plots is the bandpass filter, which is shown in black. I'm sorry, these are model independent observations of model independent reconstructions of the thing that we see. So there is also model dependent one, which is shown in orange, and that seems to fit the model independent one. It knows nothing about generativity. The CWB or the base wave, which is in purple, they do not know anything about generativity or the gravitational waves that are produced. And you can see in LIGO Livingston, to some extent in LIGO Hanford too, a complete consistency of the waveform reconstructions from the 3 different methods. That gives us pretty high confidence that these are astrophysical events. How they are produced and what are the characteristics, I'll tell you in a minute. But this was just to show you that we are pretty confident that these are astrophysical in nature. The bottom left plot, sorry, the bottom plots are the usual time frequency representation of what we see. And you don't see the usual chirping signal with power in low frequency, slowly raising, reaching crescendo and merging, producing a time frequency curve in which the frequency increases, the amplitude increases. You don't see that. You simply see 2 blobs occurring completely unstructured. Virgo does not demonstrate it at all. It's completely consistent with noise. Whereas LIGO, Livingston, and Hanford seem to have these blobs in the time frequency, but more importantly, they seem to have a coherent signal for only about 10 milliseconds. So that's the discovery. So what is this mystery signal that we have discovered? If you believe that they are gravitational waves from binary black holes, then this is a real whopper. Because the total mass of this system is about 150 solar masses. It is the most massive binary black hole that gravitational waves have discovered. There are, of course, other binary black holes in candidates in the electromagnetic observations. And in the process of merger, the system lost 9 solar masses. Hey, let me say again, 9 solar mass converted to pure space-time ripples. I think that's remarkable. There's no mechanism that can convert energy so efficiently. So these are energy-producing machines, unlike anything else that we know in the entire universe. The primary companion, probably also the secondary companion, has mass that fundamental physics says should not exist. They are in what is called the pair instability supernova gap. And astronomers and fundamental physicists tell us that these systems cannot form by stellar evolution. Maybe they did not form by stellar evolution. As the infographics on the left, you see at the bottom, a pair of black holes first merged to form the secondary, another pair merged to form the primary. And maybe they all existed in the same environment and they came together and merged. This is the most favored explanation, but maybe this is not even a binary black hole. I mean, this may be another type of event that we are discovering. To me personally, I think they are binary black holes. But there are other explanations for what this is. Maybe it was not inspiraling. It was on an eccentric orbit and they came together and merged, or maybe it's a head-on collision. There are all sorts of explanations with which it is also consistent, but probably not as much as an inspiraling binary. The remnant might have produced an EN counterpart. I don't have time to go into that, but this is still debatable. I think I'm 3/4 of the way through my talk, so I want to spend the next 15 minutes telling you about future runs and future sensitivity, or future detectors most importantly. Over the next couple of years, we hope LIGO and Virgo will reach their design sensitivity. This is indicated as late in the graphic here. And then the design sensitivity might be reached soon in a couple of years. But beyond that, there is already plan to upgrade LIGO and Virgo to what are called A+, advanced plus sensitivities, with a factor of between √2 and 2 improvement in distance and a cube of that in volume. Those are very important improvements. They will take place between, the construction or the implementation of that will happen over the next few years, and the data might come somewhere in 2025. But maybe one will be able to run these detectors up to 2030s. By that time, they would have reached something like 3 decades of operation, much longer if you also include construction. They will be reaching the end of their life. So we need to start thinking about what are the opportunities to build new detectors. But why do we need new detectors? Have we already not made phenomenal discoveries, and maybe LIGO and Virgo will continue to make discoveries, and we should not worry. But if you look around in physics, physics is really in crisis. There is the black hole information paradox, according to which information that gets into a black hole is completely lost forever. That is inconsistent with quantum mechanics. According to quantum mechanics, quantum states evolve by Hermitian operators, which means you cannot really lose information. If you put in mixed states, you can have to get that information out. This is a topic that we can really discuss for hours. It is something that's not very well understood. The Hawking radiation that comes out from a black hole is a pure thermal radiation, and therefore whatever information that went in, whether you put in different types of matter, dark matter, or you put in baryonic matter to make black holes, you seem to get out the same radiation eventually, and the information is lost. So that is troublesome in physics. So inconsistency between quantum mechanics and general relativity. Also, black holes seem to, at their center, host a singularity. One might think, okay, we are covered by horizon and we cannot see inside a black hole, so we probably don't need to worry about. But all prediction that we can make for an observer that fall with the, a freely falling observer that ends up at the singularity will encounter infinities, and that's really not acceptable. And also, there has been no viable quantum theory of gravity. There have been attempts both in string theory, but also quantum geometry or the loop quantum gravity. But so far, neither of them have produced a viable theory of quantum gravity. But the hints probably have to come from observation. And the previous two crises that I talked about, black hole singularity and information paradox, might be solved by quantum gravity. But we don't have a firm theory yet. Most recently, we have discovered accelerated expansion of the universe. But also it is the recent expansion. That means at redshift of z equal to 1, the universe seems to be accelerating. The nature of this is not completely understood. It is given a name called dark energy, but we don't know what dark energy is. The Planck satellite measured with spectacular precision what the microwave background sky looks like, and the fluctuations that we see seem to indicate that most of the matter in the universe is composed of dark matter, and normal matter is only 5%. But the significant component of energy density in the universe is composed of neither of these two, but something we call dark energy, which might be a cosmological constant. But there is a problem with that, because if you look at high energy physics, the vacuum energy that is generated by theories, either it is too large compared to the observed energy density or too small. I mean, I've seen papers arguing either way, and that is a problem. We don't know what this dark energy is, whether it's really cosmological constant or it varies with redshift. And something that we talked about right in the beginning, the same Planck observations determine what is the Hubble constant, that is the expansion rate of the universe currently, which is shown in the fourth line on the top in the right-hand most plot, it shows the Planck observations for H naught. The y-axis, of course, has no meaning. It's only the x-axis, which shows you Hubble constant in kilometer per second per megaparsec. And what you see there is that the Planck observations are pretty tight. It is 67.66 plus minus 0.42. Whereas if you look at the so-called shoes measurement, the distance ladder indicated in pink, which is a few lines below, that's about 73.24 plus minus 1.74. These two are considered to be the most accurate measurements that we have by two different methods, so-called early universe measurement and late universe measurement. And they seem to be in contrast with each other by more than 4 sigma. The other measurements, which are not quite as accurate, but some of them are consistent with one or the other, but we need to resolve this tension, but it might be hinting towards new physics. And that's the reason why it is so exciting to be able to look at it. Finally, this is just astrophysical thing, but maybe it's to do with fundamental physics. Every galaxy that we observe, including the Sagittarius A star, for which we saw a Nobel Prize being awarded, we see stars going around the Sagittarius A star. Pure space-time of nothingness. There seems to be nothing there as far as electromagnetic observations are concerned, but stars are going around. And if you measure what is the mass of the object at the center, it's about 4 million solar masses. Now, every galaxy in the universe is believed to host at their center these gigantic supermassive black holes, the origin of which has become pretty challenging to explain. How they formed, whether they formed in the very early universe, primordial black holes, or they formed by stellar processes and grew up in course of time is a question of debate. All these things mean that we have an opportunity to explore these things by using future gravitational wave observatories. As I mentioned, not just future ground-based detectors, but also space-based laser interferometer space antenna and pulsar timing arrays. I'll be restricting myself to only the ground-based detectors, just to summarize in the next few slides. But we should be thinking about all these different frequencies, the high frequencies, which are like gamma rays, the mid frequencies, which are like ultraviolet, but they are future detectors. And then the low frequency, which is like optical, LISA, Tianquin in China, and so on, and ultra low frequency. These are the plots that explain to you what are the sensitivity progression that you see on the top left corner. Here you have sensitivity progression from advanced detectors, only LIGO is shown, but Virgo is similar, to Einstein telescope and cosmic explorer. But we definitely need something in between. As I mentioned to you before, by 2025, we will see the advanced plus detectors being operational. They may continue to operate until 2030s. But these next generation detectors may not be operational until 2030, mid 2030s or even 2040s. So we do need an upgrade in between, and that's called Voyager in this plot. And if you are somebody who is working on gravitational waves, you should be worried about not having data in the mid 30s. And therefore we should really lobby for having upgrades to current detectors of the type Voyager in between. Now, the right-hand plot here, the middle plot shows you the redshift up to which we can see binary objects, neutron stars and black holes with different detectors. And as you can see, the horizon distance is far beyond where individual objects can be recognized by electromagnetic observations. But gravitational wave observations will identify individual objects occurring at those distances, redshifts of 50 and beyond. The right-hand plot shows you where we are currently. O3 is shown in just the white. I'm sorry, O3 is shown in light blue dashed line. As you can see, it is really covering the tiny part of the universe. Nothing really, as far as many neutron stars are concerned, we really don't explore anything at all. In dark blue, what you see there is the sensitivity of the advanced detectors when they reach the design sensitivity. But as you improve the detector performance and build these third generation detectors, Einstein telescope and Cosmic Explorer, you have the opportunity to view the entire universe in black holes and neutron stars. Especially when you go to the second stage of the Cosmic Explorer or Einstein telescope, you cover the entire universe for these objects. Now, what can you do with them? These are, infographics, I would call. I won't go into any details, but straight from exploring early universe space transitions, which will be seen as stochastic backgrounds and offering us an opportunity to look at phase transitions in the early universe and so on, we should be able to explore all sorts of things, such as whether black holes that we see are primordial in nature. If we begin to see black holes before any first stars formed, that's a hint that maybe they originated in the very early universe. Now, there are many things that we can discover, including quantum origin. Unfortunately, I'm running out of time, and I will take any questions during question time. But we will be able to explore astrophysics, fundamental physics with gravitational wave detectors. But let me leave you with a slide that shows you what the future of gravitational wave astronomy holds. With that, thank you for your patience, and thanks for the opportunity to share some excitement of recent discoveries. Thank you.
Thank you very much. I think we would like to ask some questions. I hope we can afford some time. If you can stay with us for
absolutely
a moment. Yeah. I can see Chris Belczynski has a question. Chris?
Can I?
Sure.
Okay.
Hi, Chris.
So I would like to comment on what we can and what we cannot do in astrophysics in terms of black hole mass formation. Okay?
Okay.
I'm sure you're expecting that comment. So,
of course.
And I'm saying that fully consciously. So unfortunately, and this is important, unfortunately, we can produce black holes in terms of mass in both mass gaps, in a first mass gap, a lower mass gap, and in a high mass gap. Mm-hmm. And I say it's unfortunate because it means that it hurts our information.
You think also high mass gap, but by mergers, I guess?
No, stellar astrophysics.
Okay.
There's an entire suite of papers right now that can easily get black hole mass up to 80 solar masses, 70, 80, even 90 solar masses. You can even close the upper mass gap or shift it upwards. So I can point you out to those papers. Those are last 6 months.
No, they're there. I am aware of them. But I also see papers which are claiming that this is evidence of physics beyond the standard model by some of the researchers. I would say this is a beautiful thing to see all these papers are coming out. But don't you agree that we will have to wait for a few more years before the dust settles down and we reach a consensus on what the real physics is?
I fully agree.
Okay. Thank you.
Any other questions? I don't see. I have just one very quick one. So it seems that the electromagnetic observations of gravitational waves, they can place some very interesting constraints on the physics you're trying to explore in gravitational waves. But the problem is that the further you reach, the more difficult it is to observe those things. And also the span on the sky is so vast that so far it was very difficult to chase those. So could you comment how this will improve already in next years and in future?
You are completely right. I think we can observe these afterglows and counterparts produced by kilonova only up to redshift of 0.3 with most telescopes, but optimistically up to 0.5. However, short gamma ray bursts, which is really only applies to a fraction of the events that we observe, might be seen. You know, it's maybe 1 in 100 events, binary neutron star events, or 1 in 50. We don't know what fraction might be observed in gamma rays. And then one might be able to do follow-up observations to identify what this object is. If you have a good telescope, good gamma ray telescopes like SWIFT. But those instruments may not exist in the era of 3G detectors, and we need to lobby to have such detectors as well. So absolutely, I think for the nearby events, these 3G detectors will localize sources to within 1 square degree to less than 1 square degree. So that's wonderful. Whereas for distant sources, it will be really short gamma ray bursts that we are thinking.
Okay, thank you. There's a question from Jean-Pierre, please.
Yes. Hi, Satya. Thank you for this beautiful review. If I'm not mistaken, I think you missed one very important astrophysical question. I mean, gravitational radiation from supernova outbursts.
Of course, of course, of course, of course. Yeah, I mean, it is something that is going to be very exciting if we make a detection of a supernova. Most of my colleagues tell me that you have a fighting chance, even with 3G detectors, to observe a supernova within our own galaxy. If it occurs within our own galaxy, we will learn a lot. My argument has been so far that even one binary neutron star, 1913 plus 16, was enough to secure a Nobel Prize and phenomenally improve our understanding of the world. Similarly, even a single supernova would be good enough. But the reason why we don't always include them in our science case so prominently is because nobody will give us $1 billion if you say, hey, there's a fighting chance we will see a supernova. But of course, once you build these detectors, they will be one of the primary targets that we will be making. Thank you very much for that comment. And
Okay,
sorry about
thank you.
missing it.
Okay, I agree with you. Thank you.
Yeah.
Thank you. I don't see any more questions, so we will not keep you any longer. So thank you very much for this amazing introduction to this field and for your talk. And we'll continue on this topic over next seminars. You're, of course, invited to join and listen to our talks as well, if you can afford it.
Yeah, please do send me. I mean, if I have time, I'll definitely come. Yeah.
Thank you for joining, and I invite everyone else to join us next week. I hope it will work on YouTube as well. Okay, thank you.
Thank you. Take care. Bye.
Bye.